the following weeks and months. So do remember that we have another seminar on Monday, March 3rd at 5 p.m. With Leonardo Impit, currently of the Digital Humanities program at Cambridge. And then just 4 short days later, we will be having our Day of Digital Humanities, which will be in person, hosted by the university library, and will feature keynotes by Barbara McGilvery and Tim Tangolini, also like our speaker today, of UC Berkeley. So do put those dates in your diaries, March 3rd and then March 7th. And please do remember to register and attend. So I'm looking forward to seeing many of you there. With that out of the way, I'd like to introduce our speaker for today, Professor David Bamman, Associate Professor in the School of Information at the University of California, Berkeley. For those of you who are familiar with, I guess, digital humanities and NLP, he will probably need no introduction, but he has a very interesting background that I'd like to say a few words about nonetheless. I guess he started off life as a classicist, so that's Western classics, Latin and Greek, and worked for a number of years for the famous Perseus project, which is still widely used by classic students around the world. He followed that with a PhD from Carnegie Mellon, and has worked at Berkeley since 2017. He's been involved in a lot of really fascinating projects and has produced many influential articles. I commend you in particular, of course, book NLP, which is widely used, and some of his very interesting recent articles, including an article in PNAS entitled "Measuring Diversity in Hollywood Through Large-Scale Computational Analysis of Film." So a fascinating and very relevant topic, as well as a preprint on arXiv, which I'm looking forward to reading later today when I have a moment, on classification with large language models in cultural analytics. So this is our distinguished speaker, Professor Bamman. David, the floor is yours.
Right. Thank you, Mark. Thank you so much, Stuart. And then thank all of you, too, for letting me talk in this space. Thank you for this invitation. I really look forward to hearing your feedback on this work, which I think really is at a really important intersection between very traditional things that we do in making sense about humanistic context and this current phase that we are all now in of the era of large language models. So yes, I think Stuart did a great introduction about who I am. My work I see as being squarely in the space of cultural analytics, right? About trying to use computational models to reason about cultural things, right? Cultural artifacts in particular, whether they be works of literature that are written in text, films like our work in PNAS from a couple of months ago, images, paintings, all of this I see as being a really interesting intersection between computation and culture. Now, for a lot of this work in cultural analytics, and I would say even in the digital humanities more generally, a lot of this work is really concerned with this core idea of measurement. Right? How do we go about designing some kind of algorithmic device that allows us to measure some construct that we care about and whatever these cultural artifacts happen to be? Right? To take an example, how do we transform an entire novel like Tom Sawyer into a quantity of interest? Right? To take that example again, Tom Sawyer is a very long book, lots of complexity, lots of interesting things happening in it. But a lot of this work for measurement often requires us to reduce this complexity into a single number like 0.53. Now, for this may seem to be an extraordinarily simplistic reduction of the amount of information that was present in the original work to get us down to this single number. But for all of us who are doing work in this space, and for all of you who are doing work in this space, I think you understand the kind of art that goes into this process of reducing this complexity of the original work down to this single measurement, right? We have to make choices that we see as being defensible. We have to make assumptions that we think are merited for the kinds of problems that we're trying to resolve. But again, it still is a reduction of information more generally. Now, once we have this kind of reduction, we're able to measure really interesting things, right? When we're able to take this complexity of the original object and transform it into a statistic that we can then go about testing for various hypotheses that we really care about. Now, over my career, what I've used this basic paradigm to measure things like the amount of screen time that characters get across different media as a function of their gender. Right. What we found in this work or this stream of work is that men are often depicted as characters as getting about 3 times more attention than women as characters do, whether we're talking about works of English language fiction over the past 200 years or Hollywood movies over the past 40. I mean, it's kind of amazing how persistent this phenomenon is that in whatever media we're talking about, men really are represented about 3 times more often than women. Um, Very strong indicators here about what the source of the problem is, right? So we find that women as authors of books tend to give equal screen time to men and women as characters, but it's really the men who are the problem across both of these spaces, right? Men as authors give 3 to 4 times more screen time to men than women as characters. And of course, most Hollywood movies, 96% in fact, are directed by men. And we see that kind of similar disparity. So we found, again, this way of transforming this really rich, complex cultural object into a single number, right? The amount of screen time that a character gets to learn something really fascinating about gender representation on film and in fiction. And we've also used it to measure things like the fact that women tend to be portrayed as occupying domestic spaces in fiction more often than men, but that women as characters are still depicted as being relatively mobile or capable of mobility. They do move around in the context of a work of fiction as much as men do. Also, from some earlier work of ours, we found that women are depicted as the linchpins of information flow within English language novels. So information gets passed from character A to character B to character C. It's often women who are that intermediary that pass information across and really propel the plot as a function of that change. So from all this work, cultural analytics really is concerned about measurement because it's only by being able to design algorithmic devices that perform this measurement that we're able to get at these basic empirical facts, right? To transform the text into a number through a measure in order to be able to derive some knowledge about them. Now, for lots of this work of measurement, I think one of the really central devices that we use for making sense about these works, as we reduce this tremendous complexity from the original source, whether it's a movie or a book or a novel, into a single number, is the basic act of classification. Now, classification on its own is really just an abstraction, right? It's simply this process of transforming an input text, an input movie, an input painting, through a function that outputs some choice among an innumerable set of categories, right? Classification is just this abstraction of mediating some input into an output choice. Now, for a lot of work, as we think about the design of classification models, many people throughout the past 50 years often think about the tension that exists between predictive accuracy of classifiers and the kind of interpretation that we want to be able to get out of the act of classification in the first place, right? To take one example here, of the use of classification simply for its predictive power in order to replace human labor, Right? We could think about examples like the experiment that the Library of Congress in the US ran a couple of months ago, looking at the power of LLMs as being classification devices to say, well, we could think about using these models or any classification system to output as that choice of a category the subject classification for the work according to the Library of Congress classification, right? To take an input here being a book, right? In this example, Bacher and Starr's very important work on classification, sorting things out, pass that through this arbitrary function that performs classification to get out of it a choice of knowledge, comma, sociology of, right? Replacing humans in that way, right? And its merely predictive capabilities. We can think about classifiers as being capable of this. Now, if we think, though, about the ways in which we see classification being used by researchers who are carrying out this kind of work in the context of cultural analytics, it's very rare for us to think about classification being used in this merely instrumental way. Um, to back off a little bit, we can also think about this other challenge that exists within classification, is that we don't necessarily need to think about classification as being something that is fully learned in a supervised setting, right? Again, this mirror function of classification being an abstraction means that there's many different ways that we can perform classification. Right? The earliest systems tend to be rule-based, so that in the context of Bacher and Starr's work, an example of that would be to say, if we see the word epistemology anywhere in this text, let's go ahead and classify it as this particular category, knowledge, comma, sociology of. Right, over the past 30 years, we've seen classifiers be much more learned, right, where there is data that comes in the form of input-output pairs that we learn what that functional set of parameters are within this abstraction that allow us to transform this input into an output. Now, with the rise of large language models, we can see this kind of distinction between rule-based systems and learned supervised systems as being kind of mixed here for these ends. Right? Because the main ways in which we see people interacting with LLMs is through the use of prompting. Right, where prompting is no longer a case where we are updating the parameters of our model based on supervised examples, but one that really does exist in between that space. But in the context of cultural analytics, it's very rare for us to see the use of classification merely for these kind of instrumental means. So what I want to talk about, at least in the first half of my talk today, is our work from this paper that Stuart also just mentioned. It was on arXiv, but it's also been published at the Computational Humanities Research Workshop that took place in December on looking at the different ways in which we see classification being used specifically in the context of cultural analytics. And I often describe this work as being a real labor of love. Because what it involved was us, so me, Kent Chang, Lucy Lee, and Nai-Tien Zhou, reading through dozens and dozens of papers that are published at venues like the Journal of Cultural Analytics, Digital Humanities, the various ACL conferences, the Computational Humanities Research Workshop, to really survey all of the ways in which we see researchers today using classification in general beyond those merely instrumental means. And so what we came out of this was a classification itself of the use of classification. I'm going to talk about each one of these different uses in turn over the next couple of slides. But to set the stage, the big uses that we found in our reading of all of these papers by researchers in cultural analytics include the use of category sense making, theory testing, challenging category boundaries, assessing category coherence, using classification for search, right, a kind of classification-assisted close reading, and then also using classification for labeling at scale in a way that's still slightly different from that merely instrumental means that I just talked about. But let me give you an examples of papers that are performing each one of these different acts of classification. The first use, and I think by far the most widely used use of classification, is its use in category sense making. right? This idea that we're often designing classifiers with data that's been labeled in some way to train those classifiers to recognize the difference between the classes, not because we care about the actual prediction itself, but rather because we want to interrogate the models and understand what the boundaries of the categories are that we are starting out with. So one example of that comes from Vian et al.'s paper from, I think it was the CHR conference last year, on building classification models to predict gender in French literature. In this case here, the input is a description of what those characters are doing, what's happening to them, right? Typical book NLP style features that are then used to train a classifier to predict whether or not that character is a man or a woman. And again, in this case, the prediction itself is somewhat irrelevant, right? You don't need to have a classifier that makes this prediction because you care about the gender of characters where that information is unknown, but rather because we want to understand what are those kind of gender biases that exist in what characters are doing or not doing in French literature as a function of their gender. And so what this work found was that women are often depicted as crying, as loving, and as kissing, as telling, as looking in ways that are much more characteristic of their depiction than of characters who are men. So again, the gender prediction itself is not really necessary here. What's really required is an understanding about those boundaries of gender that you see through classification itself. Now, related to that is the second category here of using classification for more formal theory testing. And what this often involves is stating some hypothesis upfront and then using classification as a kind of device to test that hypothesis. And this often comes as a formal test between a feature and the category that you are classifying. In many cases, this is often framed as being a test where you examine the coefficients of a learned model and see if they're meaningfully and statistically different from zero. So examples of that include Piper and Bega's work on narrativity, right? What are those features of a text that makes it seem more story-like to humans than not story-like? And there they articulate a theory about agenthood, about the use of past tense verbs, and the concreteness of those actions to then test whether or not those features are actually the ones that are predictive of this particular phenomenon, right, of narrativity in general. A third category, and one that I find probably the most interesting myself, is the use of classification to challenge category boundaries. And this is a little bit different from that first use, which just tries to circumscribe those boundaries in the first place. This use of classification starts from some initial set of categories and trains a model to understand what uncertainty exists between those boundaries. So one of my favorite examples of this comes from Peter Broadwell's work with Tim Tangerlini, who Stuart also mentioned, and David Mimno, called The Telltale Hat, Servicing the Uncertainty in Folklore Classification. What this work did was train a generative model, so a naive Bayes model back at the time, to differentiate between different categories of folk tales. Again, not because it was the actual prediction, the classification itself that mattered, but rather the points of confusion. So in this case, there are many folk tales that are about witches that are also confusably about revenants as well, right? There's something that is porous about this boundary of the categories that is itself an interesting phenomenon rather than just the mere prediction of those categories on their own. Now, related to this use of classification for challenging category boundaries is using it to assess the coherence of the categories, right? How much that category on its own makes sense as an object of classification in the first place, right? Under this basic assumption that incoherent categories should be unpredictable. So if you train a model to be able to differentiate between categories, and you have reason to believe you should be able to do so, but find that you cannot, there may be something interesting there about that lack of coherence as being evidence itself. So Ted Underwood, Sabrina Lee, and I use this method of classification in our work on the transformation of gender in English language fiction, where again, what we did in that work was to train a model to predict the gender of characters using book NLP style features again. So what the characters are doing, what they have done to them, what attributes are being used to describe them. And the important thing here was to have a classification that was given the same amount of data in a given slice of time. So in this case here, slices of time all the way from 1800 up until 2000, the same amount of data for each one of those time slices, train a classifier within the time slice to try to predict gender. And what we found in that work was that as you move forward in time, you see those classifiers less able to predict the gender of the characters, right? Giving us some information that the gender itself is becoming unstable as a construct as we see that movement through time take place. It's no longer that organizing force throughout the narratives that we can see simply as a function of those classifiers becoming less accurate given the same amount of data over time. Again, the category itself of gender we see becoming more incoherent or more incoherently inscribed in what the characters are doing over this period of time. Fifth example of these uses of classification come in what I like to think about as being classification-assisted close reading, which is to say you can train classifiers to predict phenomena in text at a relatively low level of granularity, like paragraphs or sentences, and then go about using that classifier not because you care about the category itself, but because it gives you that point in the text where that concept shows up. One of my favorite examples of this comes from work by Daniel Wilson and others at the Turing Institute, looking at atypical animacy. And I'm going to talk about this concept a little bit more in detail later on this talk, but it is the task of trying to identify when a machine is being depicted as a human and vice versa. So in this case, classification-assisted close reading means training classifiers that can identify these moments when machines are being depicted as humans, and then using that trained classifier to make a prediction about all of the machines mentioned anywhere in some large collection of text. Right? If you find those places where this atypical animacy takes place, then you can go about using traditional methods like close reading to investigate them more fully. Right? Again, tossing aside the classifier at that point for having served its purpose of just getting you that smaller body of text to close read and build your argument with. Final example I'll mention here is actually more related to that original instrumental use of classification, or the goal, I should say, of predictive accuracy for classification. And that's simply using classifiers for some downstream sense making and not just using it for the inherent sense making of the previous 5 categories. So one example of this comes from Hoyt-Long and Richard So's work on turbulent flow, where they built models to predict stream of consciousness text, not because, again, they care about stream of consciousness itself. They do. We'll use some of this work later on this talk as well. But then using those models to predict stream of consciousness and relating that to the prevalence over time is something that, again, you often simply need to have really accurate models to find those poems and those pieces of text that are stream of consciousness in order to be able to identify this association between time and genre and country as they do in that work. Now, across all 6 of these different facets of how researchers in cultural analytics are using classification right now, we saw 2 different cross-cutting goals. Right. I don't want to put these on a continuum where we think about them being in opposition to each other, because I think it is much more of a multidimensional space that we see these goals being realized in. But the goals themselves are ideally to have a classifier that has high accuracy, right, that does have that kind of fidelity of representation for what that original data is and how it's been labeled to then recreate those human judgments in a way that we see as being valid, but also has some potential for sense making, right? For us to be able to understand what those basic categories are in a way that aligns with why we're using classification in the first place. right? Not simply to make the predictions because we care about the predictions, but because we care about the phenomenon in the first place that drives the predictions and that drives the labels that we see for those categories in data. What I want to do now is talk about both of those different goals in turn and how we are thinking about those in this particular work. Now, if we think first about this goal of having high accuracy for our classification models, um, traditionally, right, for the past 30 years or so, the way that we as researchers in cultural analytics and in the digital humanities, I'd say more generally, have thought to design these kinds of models really relies on supervision, right? We have data that comes in the form of an input text and a label that often comes from some human judgment, right? Or is found from nature. And what we've done then is use a variety of different supervised models to go about transforming that input into the label, right? The text into the label to learn the parameters of that abstract function that I talked about at the very beginning of this talk. And in doing so, we are able to draw on dozens of different models that exist in the world. And in the space of machine learning and data science and NLP and computer vision, there's lots of models that exist that perform this kind of mediation. Right, scikit-learn just has dozens of them, even within that one scikit-learn package, right? That Python package, right? From linear models to nearest neighbor style models to decision tree based models like random forest, lots of different models out there that we have been using over long periods of time to learn these classifiers in order to serve all those functions I just described. However, over the past 3 years in particular, what we've seen is a real phase change happen. Right? Things are just very different now than they were 3 years ago. We've seen the rise of lots of different models that come from places like OpenAI, from Anthropic. We've seen models from Mistral, from Meta, from Gemini, from Google, that all are really upending this basic notion of how we go about learning classifiers or performing the basic act of classification, right? No longer a situation that necessarily requires a lot of supervision, right? Of course, it is still possible to fine-tune all these models using parameter-efficient fine-tuning, using low-rank approximation, but by and large, we're often using them simply as prompting models, right? Giving that kind of supervision in the form of shots, right? Examples of the kind of behavior we want these models to perform, and not necessarily requiring that same size of data that supervised models tend to require. Now, at the same time, however, we all know that there are big issues with these models, mainly in terms of, well, I should not say mainly, but one of those issues is the issue of cost on many different interpretations of what that cost means, right? Both for financial costs of the APIs or the GPUs that were required to run them, the environmental costs for what those models and those GPUs are doing to the environment, but also in terms of the basic bias and hallucinations that we all know that these models have and has been shown time and time again. So in light of this big change, right, in this way in which we see large language models being really useful for a lot of different goals and tasks that we as everyday users care about, what kind of use do we need to understand for their application for cultural analytics in particular, right? Given these kinds of costs, right? And given that we know that there are trade-offs that often exist between accuracy, interpretability, and these general financial, environmental costs, how do we make that decision about what kinds of models to use? Now, that gives this first basic task that I want to really address first. Right? When is it that we actually really need to use large language models? And when is it that simpler, smaller, and more interpretable models would suffice for the ends that we really need? Now, to start answering this question, we drew again on this reading that we did of the vast amount of research that's out there in the space of cultural analytics and digital humanities to gather 10 publicly available data sets that are in the papers in cultural analytics. And so we drew 10 of them here that are all on this slide, along with the citations for where you can find those works originally in their original articles. I'm going to talk about atypical animacy, haiku, and strangeness a lot more in a couple of slides, but it also includes work on predicting the emotions of characters as they're mentioned in text. This is data that comes from Kim and Klinger 2018. Folktales predicting the folktale ATU type from a description of the tale itself, trying to identify the genre of a passage of a work of literature, so whether it comes from a Western, a science fiction work, a detective story, and so on. Hippocropus is work from Martin Sapp and others in 2020, where the task there is trying to identify whether a story was imagined or recalled, right? Whether it was made up by the writer or it was a recall from an earlier point in their lives. Um, we also took as a task the work from Ted Underwood in 2018 on measuring how much time is passing in a given work of fiction, a 250-word passage. Not quite classification because it's predicting a single real number, so it is technically more a regression, but in the spirit of what we're trying to measure here as well. And then also Long and So's work on predicting stream of consciousness. I will note that all of this data is now publicly available on this GitHub repository, so please feel free to go use this link, use this data for whatever it is that you like. And in this case too, we made a couple of important decisions to try to really isolate the target construct in each of these data sets. And that often involved stratifying the data across groups so that the same author, for example, wouldn't appear in the training data and in the test data or in the development data, right? To make sure that it's stratified in a way that the accuracies that we're able to report really do reflect the performance for that specific classification task and less likely to be impacted by other things that might have been correlated with that work in the first place. So again, I encourage all of you to go out and use this data if you like. But what this data gives us now is a way to start assessing those kind of trade-offs that exist between all of the different kinds of models that we might want to assess the performance of. To give you a couple more detailed examples of those three tasks that I started out this slide with, atypical anapsy, as I mentioned, is the task of predicting whether or not a given passage is describing a machine as being animate. So this is one example of one data point from this work. I will just read it to you. The worst of it was the people were surly. Not one would get out of our way until the last minute, and many pretended not to see us coming, though the machine, held in by the brake, squeaked a pitiful warning. So in this case here, we can see the machine being depicted as animate because it's doing squeaking, which is something that itself, and giving a warning, which is again something that machines don't typically do in a non-animate sense. Haiku is also one of the tasks that we uh, developed in the context here of this analysis, where the task is to predict whether or not a given poem is a haiku or not a haiku. So this data comes from Long and So's work on predicting haiku from literary pattern recognition. And this data is interesting too because it gets at this notion of poetic form that others now have also recently been examining. I'm thinking of Melanie Walsh's work with Maria Antoniak, and others that was just recently published at EMNLP and Anna Preuss. Well, the task here with Long and So's original articulation was to take data that experts had already labeled as either being haiku or not, to then predict whether or not that text is a haiku. Now, haiku, of course, for you all probably, you may know this in a way, has often been defined by strict formal properties, right? So the haiku on the left by Richard Wright is one example of this, right? 5-7-5 syllable structure. Whitecaps on the bay, a broken signboard banging in the April wind, right? Clearly a haiku among most determinations by people. But you also have poems like Ezra Pound's on the right, right? Three spirits came to me and drew me apart to where the olive boughs lay stripped upon the ground, pale carnage beneath bright mist. Right, this again is an example of a poem that doesn't have that strict 5-7-5 syllable structure, but has enough of those evocative qualities of a haiku that enough experts would judge it to be a haiku itself. right? In particular, it has naturalistic imagery, which Long and So's work in using classification in order to problematize those initial category boundaries really surfaced as being one of those defining features of this particular formal genre that the classifier itself was able to expose. Lastly, I'll give you also another classification task that we extracted from the cultural analytics published work already. Comes from work by Michael Simeone and others from the Journal of Cultural Analytics article in 2017 on the poetics of strangeness, that in particular is trying to make judgments about technological strangeness. When those technological nova, right, these moments of understanding a new technical innovation are described for the first time in a work of science fiction. So the car was attached by a cable to the airship that we had just quitted, and our voyage into a new unknown began. This is an example of a description of that technological strangeness happening, right? This fact that there's a new technological instrument here that was not described before until this moment of time. Okay, so we have at this point 10 data sets that we have stratified into train, development, and test splits that we can go about using to train supervised models and then evaluate a number of different models, regardless of their training or lack of training, on that same fixed set of test data. So the models that we assessed here come largely in two different kinds, right? They come from supervised models that are allowed to be trained on that training partition, and that includes L2 regularized logistic regression, BERT, which is, has been a workhorse for a lot of work in natural language processing ever since 2018. Roberta as being a very similar model that's been trained in a slightly different objective function, and also the Llama 3 8 billion parameter model, which is small enough for us to be able to still fine-tune all of its parameters in a way that makes it more analogous to BERT and Roberta and not used simply by prompting alone. But we also can contrast that with a number of LLM-based prompting methods, including models from OpenAI, so GPT-4o, Llama 3, the 70 billion parameter model, and also the mixture of experts model. For all of those models, we give each model 10 shots, right? So 10 examples of what kind of expected behavior we want for that classification task, and don't use any chain of thought prompting. We did some experiments and found the chain of thought does not actually help. As you can find all these details in the appendix to our paper, so we left it off this analysis here too. Now, for all of these models, for the supervised models, we optimize different hyperparameter choices like the regularization strength, the learning rates. We used early stopping for all of those supervised models that we assessed on our development data. So we do this in a very systematic way in order to be able to replicate this work and assess these models in some detail. Okay, so what do we find? If we take these three tasks that I just walked you through one by one, with atypical animacy, the majority class predictor, right? So just take that label of either atypical animacy or not atypical animacy that is most prevalent in the training data and predict that same label for every data point in the test data, you're going to get an accuracy of 64.1%. Logistic regression is better, 77.8. BERT is even better, 84.3. Roberta and Llama 3, when we're able to fine-tune all of those parameters of this smaller model, are about as good as BERT, right? No better, no worse. And the prompting models here, GPT-4o, Llama 3 70 bill, and the mixture of experts are all roughly the same. Now, this means here that the supervised models for this task are no better, but also no worse than the purely prompt-based models, whether we're talking about GPT-4o or Llama 3 70, right? They're all more or less the same. Another way of framing this is that supervised models do require a lot of data in order to be able to learn those parameters. And for this particular task, we find that we don't need to have that kind of supervision to have a good performing model. Right? The large language models themselves are going to do great at this task. If we contrast that, however, with other newer problems, right, newer categories of problem like technological strangeness, we see a different story emerging, right? The majority class accuracy there is 55.6%. Linear models so logistic regression gets you 80.5%. BERT, Roberta, Llama 3 are all roughly about the same at around 88%. But the large language models that we interact with through prompting alone don't get nearly as good of a performance compared to those supervised models. So GPT-4o in particular only gets an accuracy of 56.4, which is within the confidence interval for the majority class classifier. Right? It clearly just does not get this problem just from the 10 shots and the description of it that we give it in this context of its prediction. Right, you really do need to have that supervision that illustrates what it is this problem is meant to be and a model meant to emulate in order to be able to have something that works at all. We see a similar thing happening for haiku prediction as well. Right? Majority class classifier, 53%. Fine-tuned models like Roberta and the fine-tuned Llama 3 8 billion parameter models are both nearly perfect at this task. Right? Given enough data that comes from supervision, we can learn a supervised model that's really, really good for this. The prompting models don't get this task in quite the same way. Right, GPT-4o, Mixtral in particular, are both still comparatively good models relative to the logistic regression or the majority class baseline, but they're not able to get anywhere near that kind of performance that a supervised model really is able to get to. Right, for some tasks here, what we find is that supervision really is still quite critical in having high accuracy. Right, prompting alone can get you some part of the way for some tasks, but not for all tasks. And in fact, if we think about what kinds of tasks it is that we see this big difference on, right, between supervision and between prompting alone with large language models, we find that systematically large language models tend to perform better on established tasks, right? On tasks that exist somewhere in its pre-training data. Right, Caleb Zeems and others have found this a couple, maybe it was last year, for work in computational social science too. Right, that for tasks that exist in the pre-training, right, that exist on the web somewhere, these kinds of models tend to be really good. Sentiment analysis is one good example of that, right? Large language models through prompting alone are great at sentiment analysis, but we also know that Common Crawl and the web generally has a lot of review data on it, right? It has lots of movie reviews, it has lots of product reviews. The task of sentiment analysis exists there. But for new tasks like measuring whether there is a technological strange moment that's happening in a work of fiction, that really did not exist before Simeone et al.'s paper in 2017. Right? Doesn't exist in that same kind of scale, so large language models tend to struggle. New tasks that are newly created tend to be much better to have supervision on. What we also find is that these tasks and models do tend to be sensitive to learning rates. Right, so don't trust the defaults that you get from whatever package that you're using, right? Whether it's Hugging Face or anything else, you also want to make sure that you're tuning that on some development data too. But also critically here that even if we don't think about large language models at all, and just think about those kind of comparative supervised models between logistic regression, BERT, Roberta, Llama 3, 8 billion parameter, mass language models are generally way, way better than just logistic regression. Right? The median accuracy gain across those 10 tasks is about 12 points, which is huge. It's an enormous difference between those two. And I say this as somebody who grew up with and loves logistic regression for its interpretability, but BERT, Roberta tend to be much better just merely for that basic fact of the accuracy being higher. So this here covers at least the accuracy maximizing goals that we have for the use of classification within cultural analytics. Within this work, we also thought about what other kinds of affordances that large language models have for other forms of sense making beyond those six that we were just thinking about. Because one of the uses that we often think about for computational models in general is to help us make sense of some collection of data that we have been using models to help interrogate. Now, as one kind of experiment in this, right, a very initial experiment just to see what kinds of potential these models might have, we thought about the use of large language models, GPT-4o in this case, for sense making by trying to approximate that basic function of interrogating those category boundaries that we saw as our very first use case in supervised classification. So the idea here being, if we were to give a large language model just the entire collection of labeled data, but anonymize the labels so it had no information about what the classification task is, could it tell us something meaningfully interesting about those categories that we often see as being that initial use case in the first place? So to give you an example of this here is the sense-making prompt that we gave GPT-4o for the technological strangeness data. So again, this data is binary. A passage is either technologically strange or it's not. But here, what we just did was anonymize those categories, so it's just category 0 and category 1. So that we gave GPT-4o a lot of examples, right? A lot of examples from our data, from our labeled data, that includes the text and that anonymized label. And then asked it, using this data and this data alone, what are the textual characteristics that differentiate the classes from each other? Provide a list of bullet points of those textual features in the following format. And so we just put it in that sort of bullet point sense, category 0 characteristics, category 1 characteristics, and asked, given this data across all 10 of our tasks, to tell us what those defining features are. And I want to show you the output of this. So again, if you look at our paper, you can find the output from this model for all 10 tasks. It takes up a couple dozen pages, but I want to give you at least one example here of the output for haiku. So again, the input was the anonymized labels for all those poems, right? Category 0 or category 1, and then asked to make a prediction or to give us a description about what differentiates those two different classes. And here's what we got. Haiku, right, again, or de-anonymizing that 0-1 label to haiku and non-haiku. Haiku was identified as being concise and lyrical. There's naturalistic imagery, there's emotional and sensory language, there's a simple structure, it's personal and intimate, while non-haiku texts tend to be more narrative, have a complex structure, have mythological references, a focus on characters and on dialogue. And again, this I would say is really just a starting point, but really is very similar in my mind to how we might think about other computational models being used for exploratory data analysis in the digital humanities, right? So the use of topic models is one great example of this. We have a large collection of unstructured data. We want to make sense about how those themes are organizing it. We can see classification being used in a very similar way here, even in the context of LLMs, right? Without necessarily having that kind of scale of data that we often needed for supervised models. If we go back, however, to this varying levels of performance that we see across the different tasks, I want to draw your attention to the performance for the folktales task, which is the task of predicting for a given piece of text whether it corresponds to one of 70 different folktale types from the ATU folktale inventory. Uh, Now, we designed this again so that the train, development, and test splits all have at least 3 examples of each type. And if we trained all of our variety of classifiers for predicting this task, right, a very hard classification problem that has a really big categorization space, right, of 70 categories, that a majority class classifier is terrible, right? It's 3% accuracy. We can train learned models that get, upwards of about 40, 50, 60%, but GPT-4o, in particular, got an astonishingly high 83.8% on this task. Again, choosing for a given passage what is the correct folktale type, it's able to get 83.8%, right? Really, really high scores from a really difficult problem. When I think about this task, what we noticed was that if you were to Google some of the text from the folktale task itself, what you will often find are a lot of examples from websites that describe the folktale type by name, so in this case, the number 982, along with the passage itself, right? Which raises this specter of whether or not the results that we're getting for the large language models that have been trained on this big collection of text from the web are only doing well because they've memorized the data. And so that really reminded me in this context of earlier work that we did last year in trying to understand what those texts are that ChatGPT, GPT-4o, GPT-3, and GPT-4 have memorized in the context of their work and our use of them as measuring instruments for cultural analytics. Because for a long time, one of the challenges, my white whale as a problem in NLP and in digital humanities has been trying to predict the relationship type that exists between characters in novels. I do a lot of work on characters. Book NLP is really born out of this goal. But what that does is really focus on characters in their individual representations, right? What characters do, what they have done to them, how they're represented for their attributes. And I would love to be able to predict the character relations, right? When one character is married to another, is the parent of another, that I would love to be able to do. And I've tried. It's very, very difficult. Never been able to really do it very well. So when GPT-4o first came out, what I did was just see how well this model does at this task. So I gave this prompt to GPT-4, 4 at the time. You'll find below the text of a novel, right, the whole text. Read it, pay attention to the characters and what their relationships are to each other. I gave it the full text, and then from this novel, tell me about the 10 most frequent characters. For each of them, tell me their name, their referential gender, right? He, she, they, a short summary of the character, and then any relationships at all that they have to other characters in the story. Specifically choosing from wife, husband, girlfriend, boyfriend, sibling, parent, child, and so on. And so giving it a couple of different novels and asking GPT-4 this question, I got results like this. So for Pride and Prejudice, give me characters like Elizabeth Bennet, she's a she, second daughter to the Bennet family, sibling to Jane, Mary, Kitty, and Lydia. Daughter of Mr. and Mrs. Bennet. Right on the money. It's perfect. That's great. Bartleby, right? Bartleby the Scrivener by Herman Melville. I asked the same question, right? Give me this example as one of the characters. Bartleby is a he, pale, uncommunicative, strange scrivener. He is the employee of the narrator. That is also absolutely right. Even for contemporary novels like DeLillo's White Noise. So Jack Gladney is a character there. He's a narrator, main character, husband of Babette, father of Heinrich B. Denise and Steffi, colleague of Marie J. Siskin. Right, again, right on the money. Perfect on all three accounts, solving effectively this problem that I have been thinking about and wishing I could solve for the past 10, 15 years. At some point, though, I started to wonder if GPT-4o in particular was doing so well at this relationship prediction problem for texts like Pride and Prejudice, because if you look on the web, you're going to find 485,000 results of the very first line of Pride and Prejudice. Beyond that, you're also going to find a complete list of all of the characters in like very rich description on Wikipedia. You'll also find those characters on other studying sites like SparkNotes. And in fact, you will also find a complete family tree of those characters in that book on places like Wikipedia. So, is it really the case that models like this, like large language models, ChatGPT, GPT-4, are able to really predict the relationships that exist between characters given an input text to them? Or is it simply that they have memorized those relationships from people describing those relationships explicitly on the text, on the web? right, on the pre-training text that they've been able to learn from for all of the parameters. So we wanted to investigate which of these two things was happening, right? Was it actually able to learn, or is it simply memorizing? The challenge, though, is that we can't just directly ask large language models whether they have memorized a book and have them answer us with any kind of fidelity. We also can't directly measure the perplexity of a text and have that be our only cue because texts have different sorts of complexity, and perplexity itself is not going to be a perfectly accurate measure of that. So for this work, what we did was design a new membership inference query that we call a name close task. And to illustrate how hard this task is, I want you just to read this passage and tell me if you can guess the name of the person that's missing. I'll read it while you try to guess. At dawn, I lie in bed for a while, watching the sun come up on a beautiful morning. It's Sunday, a day off at home. I wonder if blank is in the woods yet. Usually we devote all of Sunday to stocking up for the week. Can you guess that name? Just about all humans cannot. That name is Gale from the Hunger Games. GPT-4 gets this right. It gets it exactly right. Here's one other one. Some days later, when the land had been moistened by 2 or 3 heavy rains, Blank and his family went to the farm with baskets of seed yams, their hoes and machetes, and the planting began. Can you guess this name? You know it's co-referential with his, so it gives more evidence to some names than others, but can you guess it? That name is a conquo. If you were not able to guess it, you were like practically every other human being on this planet. GPT-4 gets it right, gets it exactly right. So what we did in this case to make this a little bit more systematic was to sample 100 passages from 491 books that contain a single proper person name and no other named entities to assess how often a model gets that right. If we ask humans, as we did, to guess the names, they get exactly 0%. They get none of them right. If we predict the majority class, right, the name that shows up the most frequently among these passages, that name is Mary, that would get you an accuracy of 0.6%. So not 60%, 0.6%. So from this then, what we did was assess how well different models are able to predict this name. And we tested GPT-4, GPT 3.5, and as a comparison, merely to calibrate the performance that we have, we also tested BERT, right? We know BERT should not memorize these names. It doesn't have the same capacity that the large language models do, but we wanted to try anyway. So what we found here is that when we are asking these models to predict the name and measure out of those 100 passages for a book, how many do you get right? We find that some books are extremely highly memorized by OpenAI models. So GPT-4 in particular gets 98% of the passages from Alice in Wonderland right. It also memorizes Harry Potter extremely highly, Scarlet Letter, Sherlock Holmes, and a bunch of others as well. Mostly works, I would say, in the public domain that were published before 1928 or so, but also still a lot of works that are in copyright right now. Right, so Harry Potter I mentioned, but also 1984, The Fellowship of the Ring, 50 Shades of Grey, Hunger Games, lots of works here we see really memorized by GPT-4. And again, these are hard passages. There's only one name that's missing. And most of the times, those passages are not going to give you any evidence for whether that name that's missing is Kate or Gail or any of the other thousands of possible names that might be appropriate. One thing I will point out here is that you will note that for all of those books that the other models have memorized, BERT does not memorize any of them, right? The accuracy, the prediction is about 0%, except for 50 Shades of Grey, right? Where BERT has memorized 13% of those passages. So we dug into this a little bit. BERT was trained on the book corpus, right? In addition to Wikipedia, it was trained on the book corpus, which is about 9,000 novels that were originally published on a self-publishing website. 50 Shades of Grey also originated on a self-publishing website. Not the same one, but still, it had enough that there were copies of this work that are currently in the book corpus that the BERT model, we can say with some reliability, was trained on. So BERT, despite memorizing pretty much no other text, has memorized parts of 50 Shades of Grey. We also want to get a sense here about what the reasons are, or the correlations that might exist between memorization and how often those texts show up on the web. So we carried out a couple of web searches to see how much this was the case, right? How much this correlation exists. For every book, we sampled 10 passages at random and then sampled a 10-gram within it. So 10 words in a row. You can see 3 examples on the right from Harry Potter. And these are not passages that are significant in any way, right? These are passages like seemed to know where he was going, comma, he was obviously, right? It's not particularly Harry Potter-like, but again, this is what we want to query the exact phrases for, and then measure the correlation between the name close accuracy, right? How much a model has memorized a book and the number of search results, right? Through the Spearman rank correlation coefficient. What we find here is that there's a very strong correlation between these two things. Right? The more often that we see a work showing up on search engines like Google or Bing, or those that were created over C4, Common Crawl, and the pile, we see a very strong correlation between memorization and the number of times it shows up on those places. More so for public domain works, but still also memorized for works that are in copyright right now, right after 1928. If we look to where those sources are, right, what sources have the most copies of these works? It comes from some full text that do show up on places like archive.org, but also lots of study guide websites. So places like Course Hero, Quizlet, LitCharts, that don't necessarily give a full text like Harry Potter in its entirety on one page, but give enough of it in terms of passages that effectively reproduce the entire book in their totality that these models are able to learn from. So, but let's get to the problem with this, right? This mere fact of memorization of this data. Right. Now, the problem for companies like OpenAI is, partially a legal problem, right? That if they have memorized works that are currently in copyright, there is some open question that is currently being resolved in the courts right now about whether that qualifies as fair use. I'm happy to discuss this. I think it does qualify as fair use, but that question has not been decided right now. There are court cases. You probably have heard of the one of the New York Times versus OpenAI. There's also one here by the Authors Guild that includes people like Jonathan Franzen and George R.R. Martin, right, the guy who wrote Game of Thrones. That's also currently in its way through the courts against OpenAI right now. I'll note that this particular case cites our paper, right, this memorization paper, providing some indication that these models have learned or have memorized those works that they're complaining are in the parameters unjustly. But the real problem, again, that's a legal problem. That's OpenAI's problem. The problem for us, I see as researchers in cultural analytics, in NLP, in the digital humanities, is more about this question that we were trying to address in the very beginning of this talk. Right? How we see the downstream impact of this memorization on whether we can trust an evaluation of those models when we don't know what works are memorized, right? Which ones are memorized and which ones are not. To give you an example of this, one of the tasks that we can think about is the task of predicting the date of first publication for a book. Right, because if you look in library catalogs, like the Hathi Trust, for instance, at all of those works by Jane Austen, you're going to see a distribution of dates of publication that looks like this, where the mode is around 1900, 1910. Now, this is an issue for lots of work that reasons about digital humanities in its historical context, because Jane Austen died in like 1830 or something like that. No, 1813, sometime early in the 19th century, well before all of these books are published with her date of publication right now. Because what we often care about is understanding what that original creation date was, and not the date that a specific edition of a book that shows up in a library is. So lots of people have thought about this problem of predicting the date of publication of a text, uh, so the date of composition of the text, not merely as date of publication. So to see this as a test bed for examining memorization, what we did was sample a 250 word passage from each of our books and then prompted ChatGPT, GPT-3, and GPT-4 to infer the year in which it was written, giving two examples. Again, not because we care about the actual prediction, but because we care about the correlation that exists between the memorization of a book by these models and the performance of the mean absolute error at predicting its date. Because if it's the case that books that are memorized have a lower error than books that are not memorized, that means that if we are trying to evaluate the performance of a new model, using data that we don't know is memorized, we don't know if we should be looking at a given measure as being about the memorized books or about the non-memorized books. Right? In a real test setting, we don't know which is which. So we measure the mean absolute error here. And then I'm going to show you the correlation that exists between the mean absolute error and the name close accuracy over all of those books, along with the performance from the most memorized and the least memorized books. And what we find here is exactly this kind of problem that we were worried about. That the chart here shows the mean absolute error of a model predicting the year of composition for a given work. We want the mean absolute error to be low, right? Lower is better for mean absolute error. To compare these two, you can see that the 10% of those books that are most memorized have a very low error. The GPT-4 error is almost zero for those top 10% of books, right? Those top 50 books. If we look at the 10% least memorized books, the error is much, much bigger, right? GPT-4 has a mean absolute error of predicting about 15 years wrong on average for those books compared to 0 years wrong for the memorized ones. So again, this is the real problem, right? The books that are memorized are doing much better at this different task than the works that are not. If, however, we go back to this original question from this more recent paper that we developed that speaks to this, if we looked at the memorization of all of these different data sets among GPT-4o in particular, right? This folktale task is what motivated it, but we assessed it over all of these different tasks at the same time. We do still find very strong evidence for the fact of memorization for a couple of the tasks in those models, right? For GPT-4o in particular, right? Folktales has in fact been memorized. The hippocampus task has also been memorized. And to some degree, some of the narrativity task has been memorized as well. But what we don't see is any really meaningful impact on the task performance. So the correlation that exists here between the memorization and the performance is never really significant when we counter that by the multiple hypothesis correction that we need to do, right? Using Bonferroni correction in its most strict sense. So to wrap up here, the challenge that we see here for this task is that it really illustrates here the memorization issues illustrate the virtues that open models generally have. Right, we want to have access to information about what that training data is because it helps mitigate that kind of data contamination that we see for at least the year of composition prediction task, if not for the others. Right, being able to check whether or not data exists within a model's pre-training is going to be important for us to know how to contextualize the performance that comes out. Right? If we design a benchmark or some evaluation that tells us how good a model is, we kind of do need to know whether or not that text has been memorized in order to know whether it's good or bad. Part of this whole problem originated because when I was considering that first task of predicting the relationship types that exist between characters in a book. The first examples of text that I prompted ChatGPT for were very popular ones, right? Pride and Prejudice, Moby Dick, White Noise. These are not good barometers of performance because they are going to be likely the most memorized ones. So it's a good thing to keep in mind that the texts that are popular, that occur to you at the top of your mind, are likely also going to be the ones that have been memorized because of their popularity, right? They're popular for a reason for everyone. But it also gets at this question of whose narratives exist within these models in order for in order to think about the kind of downstream consequences that exist beyond that, right? Disparate memorization about books really does open up this question about what kinds of memorized text are contributing values that tend to be reflected in other kinds of behaviors. I like to think about this from the perspective of a writer like Cormac McCarthy, right? Cormac McCarthy writes amazing books, but they're also existentially very bleak. And to think about a large language model trained exclusively on those books and what kinds of values it has, uh, it's very clear here that the composition of those texts really can influence other behaviors as a function of what's in them. Okay, so that's a lot of things to put before you here. But really broadly, what we're thinking about with these two papers, and you can find both of the citations here if you wanted to go dig into them with any more detail. We have appendices for both that give you a lot more information to contextualize what I'm presenting here. But broadly, what we're really trying to think about is how these traditional modes of classification that really drive a lot of our work in the digital humanities and in cultural analytics are really being upended, but also providing new affordances for sense making that have been really the driving factor behind why we've been using these models in the first place. Right? With those kind of affordances, with those kind of promises, do come some threats and some peril for validity that memorization does expose to some degree, but we also want to be mindful of contextualizing those kind of affordances within those perils. So thank you all. Thank you for listening to me for this hour, and I'm happy to take any questions.
Thank you, David, for the tremendous presentation. You really covered a lot of ground, and I liked the way you ended with a sort of a topical praise of open source models, I guess, with the news this week about DeepSeek out of, I think it's Zhejiang province, isn't it?
Yeah.
And kind of the predictions that, yeah, everyone's going to move to that, and therefore, you know, we have a new sort of open source horizon opening for us. So that's
Yes. No
that'll maybe be good for the humanists as it is for everybody else. So that's good.
Mm-hmm.
So we're starting to get questions. Yes, if people who have questions, could you please type them in the chat? And it is better you have a a tab. If you could send it to everyone so that or directly to the speaker rather than just to me, so it can be sort of seen globally. But while yes, people are typing. I see a couple coming in here. Maybe I'll start with a sort of a general question then. So there's 6 categories you set out. I mean, that was a really nice way. You know, historians, we call this, I guess, sort of historiography, the kind of this kind of study of the scholarship. It's really nice to see that, because it gives you a sense of, you know, what people are doing, and then, you know, one can think of sort of possibilities for one's own work and how it could fit into one of those categories. But those categories were very sort of compelling. But as we're talking about categories, yeah, where did they? I mean, how did you come up with those categories, and what was your sort of methodology there?
Yeah, it's a good question. I would say I wish I could appeal to some more formal theorization of those categories, like grounded coding, right? To say that, you know, we read through all those articles and then derive some kind of bottom-up
Yeah,
formalization that we then iterate on over time. But it wasn't quite that formal. It really was just
yeah.
reading through papers and then noticing at a broad level what kind of patterns we saw. I think we should make it more formal to make it more empirical in that way too, to see which fraction of those papers we actually see correspond to those categories.
Yeah.
To be able to substantiate my claims about one being more pervasive than the other. But it really was much
Yeah.
more loose than that.
Yeah, no, yeah, it would be interesting to see, I guess, what's the most common application and where, one can infer, it would be interesting to put more effort into one type over another if one is
Yeah,
relatively ignored.
yeah,
Um, that would be very interesting.
yeah.
Um, and then I guess sort of as a follow-up to that, every institutional and sort of regional national context is kind of different. But I was wondering, so you seem to talk about cultural analytics as a subset of digital humanities at one point. And I'm wondering, I've sort of noticed within a sort of Berkeley world, it seems cultural analytics is a popular word. I'm sort of trying to use that over here more. But I mean, in Chinese, there's a sort of standard term for digital humanities. I'm wondering if you could
Mm-hmm.
talk about this and how, you're a digital humanist working in the information science department, sort of
Mm-hmm.
locating your work without,
Yeah.
falling between the two stools of, I guess, computer science, NLP, and then humanities on the other side. How do you sort of negotiate that?
Yeah, it's a great question. I mean, I think that I'm not sure if I would see. Yeah, the disciplinary organization, I think, is always a really interesting question. I don't think I see the cultural analytics as being necessarily a subset of digital humanities, though it is in some degree. What I like to do to differentiate the work that I see this falling under from the broader digital humanities is that it is focused more on a kind of empirical measurement that I also see as being common within lots of work in the social sciences, right? In some quarters of sociology and political science. Um, so that is itself makes it not necessarily a subset of the digital humanities, so much as something that is reaching across those boundaries to draw connections from multiple different disciplines together, whether it's computer science and NLP and computer vision or others in terms of its epistemologies. But I also think that there's not much that I see as being necessarily critical about cultural analytics as being the term that's being used to describe this kind of work. And I think that we see lots of other related terms that are doing the same thing, right? So computational humanities is one example of this. Thinking about the computational humanities research workshop that took place last December and the previous year. I want to just make a pitch for that. I think that's a fantastic conference out there. So if any of you have work that you think about as falling within that space, I think it's a great yearly venue to keep seeing the same people at. But to the broader question that you had, Stuart, about this relationship between, negotiating these disciplinary boundaries, even at the institutional level. Um, yeah, I mean, I think that is one of the real affordances of work in digital humanities and information science, is that it doesn't necessarily need to be pigeonholed in a way that those boundaries that I think about here, in this classification work as being so critical to what we're doing, right? It's using classification to circumscribe our boundaries. Um, Needs to necessarily reify what we're doing disciplinarily, right? That we don't need to have necessarily a fixed boundary of what digital humanities or information science is. It is simply the locus for us doing work that can make those connections to other corners of the campus or to other researchers, in different disciplines across the world who are doing interesting things that connect in similar ways. Um, I don't think that's a very satisfying answer. I mean, to either you or to myself, as I think about these boundaries, to say that they just don't exist for some problems, but they do for others. But I think that kind
Yeah.
of fluidity is also part of the power for this field that I think that we're all
Mm.
in, that it doesn't necessarily need to be that strictly defined.
Yeah, yeah, yeah. No, it's a very interesting question. Yeah, and I think you've got some. That's a good way to start answering the question. So we have some interesting. We have some other questions that have popped up, which I think you should be able to see as
Yeah.
well. Can you see them?
Yes,
Um,
I
I
can. Should I
yes,
read them or do you want to?
um, I don't know if you want to choose the ones that appeal to you most and start from there. That's often what we do.
Okay.
Um,
Okay.
I think there's an interesting question. Chin Son Hon has an interesting question, perhaps.
All right, I'll just read it out loud. I'm happy just
Sure,
to read
go
them
for
out
it.
loud. I'll
Yeah,
do them
thank you.
all.
Okay.
So Jinsan says, do you have ideas, directions on how to test sense-making abilities of LLMs without the effects of data leakage? For example, is synthetic data or historical texts that have been less published online helpful, or are there better ways to do this? And on top of this, do you see a way to improve sense-making and common sense abilities with new techniques such as reinforcement learning? So the first question, so yeah, how do we test how the quality of models without necessarily knowing about the memorization about them? One strategy that some people have used, specifically in NLP applications that are outside of cultural analytics, is to simply create new data that the LLMs could not possibly have seen, right? So data that it only exists after the knowledge cutoff for a model is a pretty sure way to assess its abilities. I mean, the challenge for all of this is that it really is a kind of arms race, right? That all the models are constantly being updated. So you can develop a benchmark, but it's only going to last for a year or two before you no longer have any certainty that it hasn't been fully memorized by those models. I mean, I think some of the more interesting perspectives here are to think more carefully about different forms of membership inference attacks, which, this kind of name close test is one example, which is to say, to try to design models that can test when a text is in the pre-training for a model. So there's lots of methods out there beyond the name close one, but that at least gives you some information that could be helpful for shedding light on that. Um, New way to improve sense making and common sense abilities with new techniques like RL. Um, yeah, I mean, so, all of the ways in which you see large language models being aligned is with reinforcement learning, right? So any of this work in trying to align or to take an LLM and optimize it to be not simply a language model, but something that can give you output that respects a human ranking over the preferences is using reinforcement learning. And I really don't see any reason why we couldn't simply have some more formalized sense-making task as being an alignment preference, right? That you could use those same kind of reinforcement learning from human feedback techniques to optimize models for. So yeah, I mean, I think that would be really interesting to look at. I'm just reading through some of the other ones now. Do I think AI can finally overcome those problems in your task and become a credible tool for all of us? Um, I guess it depends a lot on what you mean by credible, right? I mean, credible here, I think, is something. So I think from my point of view, for any model, the challenge is always in not trusting its outputs, right? So this is always true historically for any kind of supervised model that you use for training, for classification or any other computational task. It becomes exacerbated with LLMs that are more prone to just making up stuff. So I think some of the solutions to that is to just not rely on any model to give you an answer, but rather a pointer to where you as a human can go and find the answer. So I really think that the example of Daniel Wilson's use of classification as a kind of a close reading assister, right, to find those points in the text that you think really embody the concepts that you care about, it provides more of a kind of organization for you as a person to go and read through those texts to see whether or not they make sense or not, in a way that I feel makes any of these models, whether they're large language models or other forms, very much more akin to information retrieval systems, right? Like Google, like simply Google, right? Um, um, because in many ways, all of those systems are just sense-making devices, right? You have an information need and you're querying them to try to satisfy that need. But at the end of the day, you are the human who is trying to articulate that need in the context of a query or of a prompt. And you're the one who has to make sense of the results that come out, right? Whether it's, text that comes from ChatGPT or a ranked list of search results that you get from Google, you are still applying that same human sense-making to both of them. let's see, I'm just gonna read them out loud without even reading them beforehand to decide. Chiwei Song says, thank you, Professor Bamman, for this informative lecture. 2 questions. I was wondering, based on your findings, does it mean for a domain-specific classification task, is it still necessary to compare the performance between more conventional methods or models using your self-labeled data for fine-tuning, like BERT and LLM? I noticed you only use few shot prompts when using GPT. Is it possible to fine-tune GPT-4o using like 2,000 to 3,000 labels and limit the number of tokens? Let me see your first question first. For a domain-specific classification task, is it still necessary to compare the performance with a more conventional model? I think, oh, I see. Oh, because of this phenomenon, I'm inferring about LLMs being really good at tasks that exist in their pre-training, like sentiment analysis, right? Do you still need to compare with supervised models for those kinds of tasks? That's a great question. I think that it's always good to validate no matter what your assumptions are for any given model or task, you might be wrong, so it's good just to check. So if you have some data, some small data that you can just evaluate, it doesn't usually cost that much to try to evaluate those kinds of models given that data. Um, but it does mean that when you're thinking about the kinds of tasks that you want to devote your energies to, that maybe those that do exist in the data are not ones that you need to really think about creating a huge annotation effort to have lots of human labor give you lots of labels anymore. It might, yeah, make that risk of that kind of work seem a lot higher, where there's an opportunity cost of doing something else with that time and that labor instead. But yes, I mean, so it's true for your second question here. With the GPT prompting, with all the LLM prompting, we give 10 shots, and not 2 to 3,000 shots or any order of magnitude larger than that. Part of that is dependent on the context length that all of those models have. Now, GPT-4 and all those models have very large context lengths, but the context lengths for models like Llama or Mixtral that you want to run on your own GPUs and not on the servers that you can often pay people like OpenAI to run for you for their models, means that the bigger the context length, the much slower those models run when you're actually running them on your own machines. So I think it actually is quite interesting to think about the gains that you would have by increasing the number of shots. I don't think people have found that it's been dramatically different as you scale up those kinds of orders of magnitude, but I think it actually is, again, an interesting empirical question to see how much it is the case that more shots really do help. And again, if you have the capacity and the GPUs, again, I'm all for more experiments and more empirical things, so I'm all for it. Kaman Wong says, good to see you. May I ask how you think digital humanities can be applied to the study of history? Um, well, I mean, there's a ton of digital historians out there right now who are doing great digital humanities work for history. Um, I don't know. I don't think I would have, I wouldn't deign to have anything to offer beyond what is already being done by by great researchers in that space. Um, a question that's not quite on the side of history, but is at least adjacent to it, that I am constantly interested in are questions of intertextuality and influence, right? So how anything new, any work of art is never actually completely original, but rather built on the, giants of everybody that came before. Um, I've done some of this work for trying to predict or measure instances of textual illusions in the past. And I'm thinking about very similar things for other modalities as well. It's not history, right? But it is at least drawing on this chain of information that comes from many millennia of history to help understand the movement between ideas that I think would be really fascinating. But again, I'm not a historian. I would talk to those who know that space a little bit better for those kind of questions. I'm sorry, I see we're at 9:30 now, I think, which might be our end time.
Yes, it is. But it's good. Yeah, it's a number of questions you've had, and the fact we've still got some more questions we haven't covered, I think bespeaks the interest in your talk. So that's great. And yeah, it's nice to sort of finish with history. And maybe maybe just a very brief follow-up. is there a particular paper of yours that you would suggest if the student is interested in this question of intertextuality? You mentioned you've done some work
Yeah,
before.
I have, yeah. So I think if you Google me and find my Berkeley page, way down at the bottom, there's a paper probably around 2008 that I wrote when I was
Mm,
at Perseus that was about intertextuality for Latin
mm.
poetry. There's been a lot much better work that's built, has done work in this space since then by people, not me. But that's at least one work of my own where I was thinking about some of these problems.
Wonderful, wonderful. Yeah, I'm sure the student will look it up. Great. So we are out of time. I'll just finish by reminding you all about our upcoming talks and events. So March 3rd, 5 p.m. Leonardo Impit will be talking about his work on Renaissance art and DH, and then on March 7th, we have the day of DH, all day based in the library. So that's what's coming up. But of course, we should finish by thanking our speaker for taking the time to talk to us on a Sunday night in Berkeley, and to wish him the best of luck with his ongoing work.
All right. Thank you, Stuart. Thank you, everybody. It's been a pleasure here being with you.
Thanks a lot. Bye.
All right, thanks, everyone. Bye.